Hello everyone, welcome to the next lab of ECE573 Advanced Embedded Logic Design. So in the previous video, we discussed about the DMA and how the DMA can help the processor to perform the memory transfer operations. So in this lab, we are going to build a Microblaze and the DMA based embedded system where we will read the data from the block RAM, pass to the any signal processing IP, and the output of the IP is then received by the DMA and stored back to the block RAM. And this DMA is configured by the microcontrollers. So let's start with the project in the Vivado. We'll start with the new project. So this is lab 11 demo. So I'll select the zedboard. You can select any other board as you want. Okay, so as we have done in the previous lab, we'll create a block design. So in the block design, we'll start with the first is the Microblaze IP. So let's configure the Microblaze IP. So I'll have slightly higher local memory, and my clock is coming from outside. So that's it. Okay, so let's regenerate the layout. Then I'll just change the name of this block to our previous lab name block so that we can use the same test bench. Then the reset, I'll make it as an external. Okay, so that is taken care. Okay, so now for storing the data, we'll use the block RAM. So to configure the block RAM, we need to use the AXI block RAM controller. Since the block RAM IP in the FPGA, it doesn't have the AXI port. So we need to use the additional AXI controller, which reads the data in the AXI format and converts into the language which can be understood by the block RAM. So here we are going to use the 2-port block RAM. You can also use the single port block RAM depending upon your requirement. So here I'm connecting it to the both the ports to the same block RAM and then the AXI IP to the corresponding Microblaze processor via interconnect. So here this is my block RAM. This block RAM is connected to this block RAM controller so that this AXI signal can be transferred into the language understood by the block RAM. And what is this address? It is nothing but to communicate with any memory, you provide the address, you provide the clock, you provide the data signal, you provide the enable signal, reset and the write enable or byte enable signal, and the same thing for the port B. So basically, this is the dual port block RAM where you have the enable signal, write enable signal, address, read data, and the write data signal. And AXI is nothing but our conventional AXI port. Now, what I need to do, I need to have the DMA which will read the data from the block RAM, pass it to the IP. The IP will process the data and send the processed data back to the block RAM. This DMA will be configured by your Microblaze, and also Microblaze can write the data inside the block RAM. So via this DP port. So let's add the DMA. So we'll use the AXI DMA for this lab. So inside the DMA, you have the simple mode and the scatter gather mode. In the scatter gather mode, you can do the transaction at the non-contiguous memory. In case of the simple mode, you can do the data transfer from the contiguous memory. Okay, so that's it. So we'll use the simple mode. Rest of the things will keep it as it is. So now if you look at the DMA, you have the AXI light port. So via the AXI light port, Microblaze can configure the DMA. So it can give the DMA source address, destination address, and the corresponding the size of the transfer. Then you can see that there is a two memory mapped AXI port. So through this memory mapped AXI ports, a DMA can communicate with the memory, and then it can read and write the data to the memory. So what we are going to use is the block RAM is our memory source. So to communicate with the block RAM, we need to use this. We need to use this interconnect. So what we are going to do is that we are going to add the two more slave ports on this AXI interface. So I'm adding the number of slave interface. So once I add the number of slave interface, you can see that now I have the two ports. So once I have the two ports, now what I do, I'll connect the DMA to this port. Okay, so DMA is a master and your interconnect is slave. So you can see that for this interconnect, there are two master. One is your DMA and the second is your Microblaze. So via this interconnect, Microblaze can write or read from the block RAM, and via same interconnect, your DMA can read and write from the block RAM. And you can see that this is the memory map to stream. So from this port, DMA will read the data and then convert into the stream. This is the stream to memory map. So from this port, received data on the stream interface will be converted to the memory map interface and will be returned into the block RAM. So then we'll run the connection automation so that we can connect this AXI light port to the Microblaze so that Microblaze can communicate with the DMA and it can configure the DMA. So I'll use the AXI light port, and then AXI light port, you can see that the master is your Microblaze. Then for this one, we'll connect the 100 megahertz clock. So for the additional slave ports, we need to connect the clock. So that is taken care by the run connection automation. Okay, so you can see that this AXI light port is connected to the interconnect, and who is the master to the interconnect? Your DMA as well as your processor. So if the processor wants to configure the DMA, it will use this DP port, this AXI interconnect, and this port to configure the DMA. Okay. So now you can see that the Microblaze will write the data into the DMA and to the block RAM. Then Microblaze will configure the DMA to read the data from this IP block RAM, process the data, and write the processed data back to the block RAM. Now, using this port, you can see that there is a stream port. So you have received the data over the memory map port from the block RAM. You will pass to the stream port. You will connect your IP here, and this IP will process the data, and processed data will be sent back to this S2MM port, and this data will be sent back to the block RAM. So in this lab, first what we are going to do, we are going to send an array to the block RAM, and what we are going to do is that we will find out the square root of every element in the array. So for that, what we are going to use is the floating point arithmetic, because your square root can be a floating number even though your inputs are the integer. So integers are being passed from the Microblaze processor to the memory, and this we are going to calculate the square root of those integer. So we are going to use this floating point arithmetic IP, which can perform a different wide variety of tasks. And this floating point arithmetic IP has the stream interface at its input and output. So this, since my inputs are coming in the fixed point, I'm going to convert them to the fixed to float. So I'm going to use this IP to convert the input to the float. So I'm going to customize the IP. So you can see there are multiple options are there. You can explore those options later. So I'm going to use this fixed to float. So my input from the Microblaze are the integers, and I'm going to convert them into the floating point representation. So here I'm going to, you can see that the inputs is the integer 32. Then the output is a single precision floating point, that is the 32 bits. So what I'm going to do is that in addition to the your AXI stream, you can see that in the AXI stream you have data, valid and ready. I'm going to add the last signal, because the last signal is important for the communicating the burst of data. So you can see that now the last signal is also added in this one, and rest of the things I'll keep it as it is. Okay. So this IP I'm going to use for the fixed to float conversion. Then I'm going to use one more IP, which is again a floating point, which will calculate the square root of the each element. Okay, so I will use that IP. So add the floating point IP and then configure it. So first we'll change the name so that it will be easy for us to understand what this IP is doing. So we'll do the square root operation. So square root IP, so we need to change the functionality so that it can work as a square root IP. So you can see that here at the end there is a square root option. So you can do the square root of operation. Then the precision of input is the floating point. So input is a floating point, output is a floating point. And again, I'm going to add the last signal, because this is a good signal for the handshake operation. So I have added the floating point square root operation. So now what I'm going to do, the output of the DMA, you can see the MM to S, I'm going to connect to the input of the fixed to float. So input is fixed point integers coming from the Microblaze or the block RAM. They are converted into the floating, and the output of the floating is given to the square root, and this output of the square root IP is then connected to the DMA, and the DMA will write back the data to the block RAM. Okay, so regenerate the layout. So you can see that the rest of the things looks fine. Then we are going to connect the clock to the 100 megahertz clock signal. So this looks fine. Okay, so this is our diagram where what is the flow? This Microblaze will write the data to be processed in the block RAM. It will configure the DMA to perform the read operation from the block RAM, pass the data to the IP, and collect the process data and write back into the block to the block RAM. You can add the interrupt also. So you can see that there are MM to S, that is memory map to stream interrupt, and the stream to memory map interrupt. So whenever the reading task is performed, the Microblaze can send the interrupt, DMA can send the interrupt to the Microblaze, and whenever the writing task is performed, the DMA can send another interrupt to the Microblaze, and you can make use of that interrupt. So you know how to make use of the how to enable and disable the interrupt, so you can add that functionality as well. Okay, so what we are doing, we are getting the array, we are finding out the element wise square root of each array. Now, in the second part of this lab, what we are going to do is that we are going to create our own IP using the HLS. And what we'll do in that IP, we'll do the accumulation of this entire square root in that IP, and then the only one output will be passed to the DM. So you can create your IP in the HLS, add inside the block diagram, and get your functionality and done. Okay, so you can implement any algorithm you want. So this completes the design of the block RAM. I hope we have done or we have taken care of all the steps. So I'm going to validate the design. Okay, so there is a issue is that the slave segment of the block RAM memory 0 is not mapped to this one. Okay, so we need to take care of some address remapping. Okay, so here you can see that you are getting some memories for whom the addresses has not been assigned. Okay, so what we need to do, we need to go to that one and do the auto assign address. Okay, so then this one is done. Auto assign address for this one. Okay, so let's validate the design. Okay, so now the validation is successful. There are no errors. So let's follow the couple of steps. We create a HDL wrapper, and after we create the HDL wrapper, then we are going to generate the output products. So then generate output products. It will take some time to generate these output products. Okay, let's keep it in background. And then another thing we need to do is that we need to add the test bench so that we can generate the reset and clock signal. We are not using the GPIO, so we don't need to add the GPIO part. So side by side, when this process is going on about generating the output products, we can write the test bench. Okay, so once this adds source option gets enabled, so click on add sources. Next, either you can use previous test bench or you can write your own test bench. So this is the module for which we are writing the test bench. So let's do the module instantiation. And the instance name. So initialize the clock and reset. We are using the active low reset. And generate the clock. Okay, so this complete the test bench. We have completed the block diagram design. So after the output products are generated, we'll continue with our SDK part.